Okay, I propose that we start since we have a few presentations to go. I would like to thank everybody for joining, especially the presenters that they have accepted our invitation. This is the second webinar of the project events. We waited a bit to organize it because we wanted to have more mature results and more interesting things to show to the community. As we will mention also in the end of the webinar, we are very close to the finalization of the project. It's next month that we are finishing. We'll also show you some information about our final event. So without further ado, I would like to present our welcoming speech from our director, the Research and Development Director of ICCS and the founder and director of the iSense Group, Dr. Angelos Amditis. Dr. Amditis, the floor is yours. I believe you can see the presentation.
Thank you very much, Bill. Good morning to everyone. Very happy to be here with you in this second webinar of events, and very proud to be actually the coordinator of this project together with Vasilis and other colleagues from ICCS, a project that I consider that's really in the technological state of the art, and a project that really delivered very interesting results for all of us, but also for the wider community. So as Vasilis mentioned, we are closing to the end of this quite successful and interesting project. And I think it's quite important that the results of such projects are being shared with the community and all the stakeholders and the interested partners. And this is the logic behind this webinar. So I will give you a small introduction, explaining a few things about the project overall and the expected outcomes and impact. And then, of course, we'll go into more details with all my colleagues from ICCS and the consortium that are going to deliver to you more specifics on the actual results. As we mentioned, the project is closing end of February. It was a 3 years project, more or less, with a small extension. So overall, we are now on 42 months of duration, with a budget of almost 7 million euros. The project was all about in-vehicle perception and decision-making in specific complex environments. And to deal with this, we have created a consortium of 13 partners from 8 European countries that you see also in this map. So the project was all about designing and implementing different perception algorithms, implement them on board of vehicles, algorithms needed for safe driving of automated vehicles, specifically in complex environmental conditions. And the logic is how we could really, by using these algorithms and these technologies, we could overcome current ODD limitations that we all know exist in relation with automated vehicles. To do that, we used 9 prototype vehicles that collected data, and we used them also to assess the different perception improvement based on our algorithms. So we designed and implemented decision-making algorithms able to cope with a variety of traffic scenarios. Specifically, we look on edge cases, which is a key aspect, as you all know. And we consider in this respect potential also contradictions to existing traffic routes. And we try also to use a number of different metrics. For example, time to collision, and also the ratio between MRMs and actually the ones that were applied and the ones that were necessary. We also developed solutions for continuous perception system self-assessment. We try to focus on safe and resilient operation. And also we used and implemented logic of triggering improved minimum risk maneuvers in case we have a scenario where we are reaching the ODT limitations. And there we also worked, except of the classical metrics, also on evaluations like the appropriateness of minimum risk maneuver. Then we integrated, tested, and demonstrated all these algorithms in prototype vehicles, but also in simulation environments. We did end-to-end system tests, and we demonstrated these algorithms under real conditions, but also in simulation. Of course, in such a project, you need to assess the impact of the different developments to determine the cost-efficient sensor suits for such type of vehicles, and in order to be able to deliver the necessary perception performance, but also taking into account the cost element. And of course, we did actions like what we're doing today, disseminated and communicate the different project findings, and also we focus a lot in increased collaboration also with international stakeholders, and also with standardization bodies, as we'll explain later on. Next one. So I would give you some key results of the project in a summary, in a nutshell, some insights on our actual key results. So we performed multiple experiments. We used different setups. We used single sensor setups, but also multiple sensor setups, and we did all the needed comparisons and assessments. We used a hybrid experimental setup. We used both situations where one part did an end-to-end setup, where the vehicle exchanged information with a simulated environment, so digital twins actually, but also between partners, where one partner could run a simulation and then information is exchanged with the second partner's vehicle, which was also quite interesting. And then the project really built on a wide collaboration, both directly but also indirectly, with, I would say, the majority of running CCAM projects, both directly but also through different clusters. Next one. This is an example of one of the results of the project, something that we built here internally in ICCS, where we have created a digital twin of our campus. And then we used there a hybrid setup. First of all, a real vehicle that drives on the actual road and sending information in real time, of course, in the simulated environment, which solves along with any digital agent that we employed in this system. This allowed us to have multiple experiments and multiple variations of the same experiment using different parameters, and all of that in a very time-efficient way. So these are some of the impacts expected on this project. We'll start with some midterm expected impacts and then some long-term ones. So first of all, one of the major things that we worked with was the logic of creating cost-efficient sensor suites. And there we have done different cost-benefit analysis for different combinations. So that had a dimension both technological but also economical. Then we have worked a lot on creating advanced environmental and traffic recognition and prediction situations, the clear impact on all the people that are working on automated driving. There you have the dimension, both technological one, but also societal one. And one of the metrics we have been used there to assess this impact was to achieve decreased false detections and non-detections of vulnerable road users, but by at least 10%. Then we have been working a lot and with a clear impact on determining the appropriate course of action of an automated vehicle in a real-world environment. Again, important in terms of impact technologically, but also societally. And there we have used metrics like the comparison between appropriate courses of actions with actions suggested by our algorithms in event. Then another impact, quite important on the mid-term, is the creation of safe and reliable operations in expanding ODDs. And there we had more than 3 OEMs and tier 1 suppliers interested in building on events results. And this shows exactly the impact of the work of event. And last but not least, on the midterm, always the standardization mandate for performance requirements for environmental perception systems with regard again to different automation levels, but also different ODDs. And there I'm proud to say that at least 2 relevant working groups in standardization consider different inputs coming from our project, from events project. Last but not least, on the long-term level, we have been working on impacts related with validated safety and security, improved robustness and resilience, which again is a very important aspect. And there we use the metric, between other things, of decreasing by 10% the critical cases where automated vehicles are involved. Then another important impact is a secure and trustworthy interaction between this time road users, automated vehicles and conventional vehicles. And there we have really used as a metrics the capability of high detection rates of vulnerable road users and other projects, the limitation of false detections and non-detections by at least 10% on what the different references are shown. Important also, and with a quite clear long-term impact, is the logic of creating a better coordination of research and innovation and implementation with large-scale testing activities in Europe. And there we have managed to exchange information and liaise with other CCAM projects on a regular basis, including the flagship CCAM project, High Drive, not only that has been working in parallel with events. Last but not least, one of the important impacts that we expect from a project like events is the supporting the European leadership in the development and deployment of CCAM systems. And one of the metrics we use there is the support of the project, of the findings of the project in creating highly skilled jobs in automotive industry. So that's it from my side. I try to give you an overview. The details will be shown now from my colleagues. I hope I give you an idea of what is the project about, what are the key results, and what are the impacts of this quite significant project. Thank you very much for your attention. Bill, back to you.
Thank you, Dr. Amdidis. I will give the floor to our to the moderator, let's say, of today's the webinar of today, Elena Daskalaki.
Hello, everybody. Good morning. My name is Elena Daskalaki. I'm a colleague of Bill and Dr. Amdidis in ICCS in the CCAM group, and I will be moderating the discussion today. So I will directly start by introducing the first speaker, which is Bill, Dr. Bill Rungas from ICCS. Bill obtained his PhD on games and simulations at TU Delft. He has over 10 years of experience in transportation and logistics in the Netherlands, Sweden, and Greece. He's currently senior researcher and project manager at the ICCS group at ICCS and CUA, and at the same time, he's an assistant professor at the Department of Communication, Media and Culture of Pantheon University of Social and Political Sciences in Greece. And he is the day-to-day manager of events. Today, his presentation will be on beyond line of sight, hybrid validation of V2X collective perception in complex scenarios. Bill, the floor is yours.
Thank you, Elena. So after Dr. Amditi's presentation, I'll try to keep up with the interesting stuff that we did in events. And this is part of the work that we did in ICCS. And it's mainly about collective perception in different scenarios and in different setups. So just a brief overview of the presentation. I will start with what was our motivation, then go a bit on the background.
Do you hear Bill?
No, I think it's frozen.
It's on his side.
Yes, he probably faces some connection issues today. The internet is unstable in Greece.
Let's give him a couple of minutes, and if not, we can maybe move on to the next presentation and come back to Bill later.
Elena, we have a problem. Yes, we have a problem. Erin actually cannot connect either, so I'm trying to fix this problem. So if Bill is not able to do it, we can go to the next speaker.
Okay, let's give him a minute. Bill, are you
Sorry,
here?
Can you hear me?
Yes, we can hear you.
Yes.
We lost you for
okay.
a couple of minutes.
Okay. Sorry for that. Can you hear me now?
Yes, I think you have to go back to the previous slide because we missed that part.
Here. You lost all of this? Okay.
Yes.
Okay. So I was saying that our main motivation for let's say departing on this journey of exploring what collective perception can offer us is that the main, let's say, and the obvious reason is that autonomous vehicles are limited by the sensors and the limitations that these sensors introduce, like the range and their inability, let's say, to see behind occluded objects. And we know that with V2X, we can share this information and we can enhance, let's say, our understanding of the surrounding environment. But a great challenge is that validating collective perception in complex and realistic conditions is very challenging. So our contribution is that we start and we mainly use a Bayesian probabilistic fusion algorithm for multi-agent collective perception. And we add to that the sort of a hybrid validation which combines simulation with real-world testing, so using both virtual agents and real vehicles. And of course, part of it is a quantitative evaluation so far in a roundabout scenario, which is realistic, and it's in an actual roundabout. So a bit of the background work and how we have, let's say, built on that is the earlier work, and it's something that I will show later that we take kind of as initial assumption is that earlier work has more focused on communication and the quality of service and latency in the communication, while more recent trends work on the fusion of different sensors in a perception level. So there is a gap on the modeling of probabilistic modeling. So the work done there is quite limited, and even more limited work done in a, let's say, in a hybrid setup and a hybrid validation of different frameworks, which allows not only to have a variety of scenarios that simulations offers, but also more realistic setups and more realistic conditions that come from using a real vehicle. So this is an overview on the right, on the image that you see, it shows an overview of the framework. So in yellow, it's the input that the algorithm gets, and that includes, of course, every data that comes from the ego vehicle and the object list that it creates, and the localization using GPS, and also the map of a specific area. Then in purple, we have the processing, and the processing for each vehicle that is included in this process. We compute the localization filter, and we estimate the field of view of the vehicle, and then we have a field of view and localization based consistency checks. And then is where the Bayesian fusion comes with assignment of Bayesian update probabilities for each connected vehicle. And then this leads to the fusion of the Bayesian for creating let's say, a global perception, which is visually represented in an occupancy grid. I will show this in the later slides. Which leads us to what's the actual output in blue, and that's the fused probabilistic occupancy grid. So this is the first step. So we discretize the grid of the specific area, and for each cell, we assign a binary random variable 0 or 1, and then what we want to calculate is the probability, using the Bayesian fusion, the probability that a specific cell is occupied or not. So using some recursive Bayesian update, as shown in the equations, we have an order invariant recursive update, and which incorporates also sensor uncertainties and localization noise. And we'll show, especially the second part, the localization noise, we'll show it towards the end where we did the evaluation. The Bayesian recursion fuses multiple observations, and that's one of the main advantages, while preserving our uncertainty estimates for each grid cell. And we do online reliability assessment in the sense that we estimate the reliability of each cell in real time using statistical and spatial consistency metrics. And that would include the covariance tracking from Kalman filters, local uncertainty indicators for critical regions, and the field of view consistency across the different agents that are connected. And this leads us to how we have validated the framework. We have taken different considerations, and that's that for each ego vehicle that we examine, we take three different, let's say, considerations. The one is to validate it without any collective perception, so only the perception of the ego vehicle. And then we have two variations of collective perception, one with two additional connected agents, so the ego plus two agents, 3 in total, and then the ego plus 5 agents, so that's 6 in total. So in its evaluation, we calculate some metrics, and that would be the field of view coverage, recurrent precision for the occupied and the unoccupied cells. And the key to that is that the above frame calculations are aggregated in an area under curve evaluation in order to be able to characterize the entire sequence of frame during which the agent, the ego vehicle is present in the scene. So the moment that the ego vehicle enters, let's say, the scene that we are examining, we calculate all these metrics until it leaves this scene. And as I mentioned earlier, all of the above is repeated from different localization noise from 0 up to 2 meters for a total of 90 evaluations per scenario. So here I have 2 videos, so this slide and the next one, showing 2 different examples. The one is on the top. So before I play it, I want to just tell you what you will see. So on the left, you see the initial grid cell. In the middle, there is it's the bird's eye view from Carla simulator, and on the right is the output of our algorithm, the collective perception algorithm, and the grid cell that is shown. So just to say a few things about the colors that you will see on the right cell, on the right figure, that is the collective perception occupancy grid, is that very dark colors mean that the cell is occupied. Very white color means that we know we have a very good probability that the grid is unoccupied, and the more gray it is, it's more unknown to us. So we don't know whether it's occupied or unoccupied. And what you will see is that the more agents are connected, the more knowledge we get about the different areas, even for those that are initially occluded for the ego vehicle. So I will just play. So on top is 6 connected agents, and on bottom it's only the ego vehicle, so no collective perception. So you see that there is much cleaner view of here on the right. You see much more white, so meaning that the ego vehicle knows has much more information about the occupied and the unoccupied cells. And moving to the next one, where again on the top we have 6 connected agents, so 5 plus the ego vehicle, and on the bottom we have 3, so 2 plus the ego vehicle. So if you compare to the previous one, the 3 is much better than the no collective perception, but still with 6 connected vehicles, there is much clearer image of what there is ahead for the ego vehicle. So here's an overview table of the evaluation that we performed. I will not, of course, go through all the numbers, just to give a general overview of what you see that, of course, the more localization noise we get, the results a bit deteriorate, but they still remain quite high, especially for the more connected agents. And we maintain a quite high precision and recall, especially even in a 2-meter localization noise. And everything shows that the more connected agents add, of course, to better results. So that was something that we hypothesized, but we also kind of found with the numbers. So to conclude what I've shown you today, I showed you is a hybrid framework that bridges simulation and real testing, and a probabilistic fusion that enhances explainability and robustness. And as I just showed, even in modest cooperation, like when we have 3 agents, we have major gains with higher reliability present even under great localization uncertainty. So our next step is to introduce dynamic Bayesian updates, latency and trust modeling, and as well as to be able to create standardized safety validation like ISO, and also conform with the CCAM messages. So as an end note, our approach supports safe and explainable deployment of collective perception systems, moving toward the trustworthy cooperative autonomy. And thank you for your attention.
Thank you very much, Bill. We will give some time in the end of the webinar for questions to all speakers. So we will directly move to introducing our next speaker. It's Professor Eren Aksoy. He's a guest professor at Halmstad University, Sweden, and he is the coordinator of the Horizon project RoadU, which focuses on robust automated driving in extreme weather. The presentation will, excuse me.
I can share my
present
screen.
RoadU, yes, of course. We'll present RoadU toward robust automated driving in extreme weather.
Yeah. Hi, everyone. Terribly sorry, I'm facing a bit of technical issues, so this is why I will also turn off my camera just to gain some bandwidth. I assume you see my full screen now, full screen for the presentation.
Yes, we do.
Thank you for confirming that. So I'm going to briefly talk about the RoadU project that I'm coordinating. So RoadU stands for Robust Automated Driving in Extreme Weather. I think that fits very well to the subject of this webinar. And also thanks a lot for, by the way, for inviting me. All right, so what are we talking about? We're talking about how to make autonomous vehicles functioning or up and running under challenging weather conditions, because we have seen already many different AV videos on the web showing how vehicles can go from A to B autonomously in very clean or sunny days. So the challenge is like when we start talking about harsh weather conditions like harsh rain, snow, and so on, there are a bunch of problems that we have to handle. I'm gonna, just to make the problem crystal clear, I'm gonna show you some examples here. We have data recording coming from the KIT dataset. So it's from Karlsruhe, city Karlsruhe in Germany. It's a sunny day. Images are visible. Also, the point cloud on the left is quite clean to some degree for perception tasks. The challenge indeed starts when we have bad weather conditions like harsh rain in this case. This is the data from Waymo dataset. It's very limited, by the way, in those public datasets like Waymo. You have only like 6 recordings, if I remember correctly. It's one of those where you have series. Please pay attention to those. Oops. Noisy point cloud data on the left bottom. So the splashing water in the front of the vehicle is just introducing a bunch of noise. Also, the camera image is not that easy to drive, even for a human. So all sensors are getting negatively impacted by these adverse weather conditions. So RoadU is just about that, how we can make vehicles functioning under these bad weather conditions. We have in total 15 different partners coming from 7 different European countries. It's a 4-year project, and we are just approaching to the last year. The project is going to be over by September this year. And we have a total budget of 10 million euro almost. And we have a bunch of vehicles, not only for data logging, but also for the demonstrations. I will show you some of those in the upcoming slides. So just briefly, RoadU addresses all these weather-related challenges by developing robust and cost-efficient embedded in-vehicle perception. So whatever we implement here, we promise to deploy them to the vehicle platforms. So this is why we talk about in-vehicle perception and weather-aware decision-making system. So not only the perception, but also the control algorithm should be weather-aware for connected and automated vehicles. So we should also incorporate we should also incorporate how to communicate among vehicles or with infrastructure to support this, so that we have an enhanced performance under harsh weather conditions. RoadU has actually 3 pillars. Pillar 1, shown at the bottom, is about collecting synthetic data and training all these AI models by creating the digital twin and so on. And before going to the pillar 3, which is about real data collection, we have another pillar in between. We call it a controlled environment. So you have a controlled rain and fog tunnels where you know the amount of noise to some extent. So this pillar 2 is bridging this gap between sim to real gap. And all this data is basically fed to our AI-based perception and control algorithms before we deploy our solutions to the vehicles. Also, we have a X-in-the-loop system where we validate and test the accuracy of all those models before the real deployment. And the ultimate aim here is to reach the TRL7 as much as we can. Now I'm going to show you some examples from each of these 3 pillars. Again, recall that pillar 1 is just about synthetic data. We have already released this simulator, WinterSim, from our Finnish partner. And it is a parametric simulator where you can just change the amount of snow and rain in the environment. You can change the conditions very easily. You can change the traffic density and so on. So this is a very useful tool to test, to generate some synthetic data. And here on this map, you can see the places, locations where we have the demo. And what we did, we created a digital twin of those demo areas. One of them is in the North Arctic Circle in Lapland region in Finland. And here you can see on the top animation, you see how this digital twin looks like. And at the bottom, you also see the digital twin of the control environment as well, like the fog tunnel, rain tunnel. And we also used generative models, AI models, to convert any kind of real image into this kind of artificial data in this pillar. So pillar 2 is about controlled environment. We have a setup in Germany where we know the amount of where we have the full control on the amount of the rain. We are basically emulating the rain. Here we have some sprinklers, and we have some buggers, and we have also wind and rain sensors to measure the amount of it. And we have a sensor ring, which is basically having multiple LiDAR cameras, thermal cameras, and as well as a 4D radar sensor. They're all automotive graded sensors. And we just put the sensor there just to see the degradation. This is basically the best sensor suite that you can find. And here I show you just some recordings. At the top, you see how RGB and thermal camera looks like. At the bottom, you see how the LiDAR point cloud is changing because of the wind, the rain, or the emulated rain is changing a lot. And what we did is we also run an automatic annotation tool, which is basically now giving you the point-wise annotations for each single point in your point cloud. And we release our data set, which is very useful because now you have points coming from not only from LiDAR, but also from 4D radar sensor. And this can be now used because you know which points belong to the noisy raindrops. Now you can use this thing to validate your mathematical modeling, rain modeling, so that you can validate how good your model is. And now I'm going to start talk about the pillar 3, real world data. This is one of our real data logging vehicles. We have a sensor ring here with LiDAR 128 Velodyne, and we have an RGB camera, and we have 3 thermal cameras synchronized with all this. And we have also one Vaisala sensor, which is an active sensor, which is giving you the grip coefficient of the road surface. Plus, we have GNSS and IMU. And what we did is we used this Vaisala sensor that I'm showing here at the bottom right as a ground truth. Okay, and then what we do here, we use RGB and LiDAR data. We fuse them, and we are trying to estimate the road grip coefficient, so how slippery the road is. And we have some predictions for this grip estimate. And then what we do, we have also some prior probability scores for each road type. And then what we do, we just fuse them together. So this basically gives us the area on the road surface which are very slippery, plus we have a confidence score. So this video is basically a better explanation. On the top, you see RGB image together with some Vaisala sensor readings. Those are very small local patches that gives you the grip estimates. But now what we do, we use camera and LiDAR to extrapolate this thing for the remaining part of the road surface. In the middle, you see that one. Here we do not use any kind of image segmentation. This is why it's basically propagating out of the road surface, but assume that you can also get the road's segments and then apply it to there. But here the idea is now, can we get the slippery area, which is yes, and then how much we can trust on that. So at the bottom, you see the uncertainty scores. For those areas where you have high slippery, the coefficient is basically low. Otherwise, it's very unsure. Another real-world application is about filtering. This is one of the best innovations that we have in the project. So we assume that your point cloud is very noisy. What we do is we do our best to clean it before running our downstream tasks. For that, we have developed one of the fastest, it's actually the fastest and lightest filtering algorithm in the world right now. We achieve also the state-of-the-art results. And the good thing is that we do it not only in a supervised, but also in an unsupervised manner. That means you do not have to go to your data and label every single noisy point, which is a cumbersome process. But now we released a version where this can be done very efficiently as a supervised method as well, in a full unsupervised manner. It's very useful because when you apply this filtering, we show that your segmentation results goes up. So you can now on the left you see the noisy one, on the right you see the filtered version. If you now send the filtered version to your segmentation, your performance goes up by 5%. Also, your object detection likewise goes up by almost more than 2%. So it's very useful, this filtering. It's like applying low pass filtering within more AI based right now. So here I show how it looks like on the real data logged by our vehicles. On the top, you see the noisy version. On the right, you see the clean one. And also here, how it looks like when we run it on our truck in Turkey under foggy and rainy day. So bottom right, you see how the point cloud is cleaned. Although the vehicles are different, you still have the same performance. So here I would like to show a bit about the control side. We have developed a controller which is more weather aware, and we also connect this thing to the infrastructure. This is done by CRF, and we have also participants from CRF in this webinar. I should acknowledge them. This is a great work from their side, and also VTT from Finland. So right now what's happening is that the vehicle is autonomously running on the road at 50 kilometers per hour, and then on the roadside we have a triggering signal. It says that the road in the front is very slippery, please stop. So then the vehicle is basically optimizing its path. It says, okay, now I should change my path. Instead of doing like emergency stuff, it is slowing down and finding a nice path to the road shoulder and goes there autonomously to park. So this is basically a very nice V2X communication, very nice example of the communication with the infrastructure to control your vehicle in the case of an emergency. So instead of doing a very naive emergency stop, you can plan based on the weather. You can plan how to slow down your vehicle and take a stop action. So basically, that is one of the innovations we have in the RoadView project. Last but not least, we have also released a very big data set, fully annotated. Those are the numbers. I don't want to bother you with those numbers, but here is an example. This is one of the this is the only example in the world that we have a point cloud labeled semantically, plus also we provide labels for noise. So here, this is the data coming from a snowy day, and those signed points on the right is the falling snowflakes. So you even know the labels for the noise points. Plus we have the bounding boxes. So you get semantic segments, bounding boxes, and noise information all in one labeled data set. So this is the one that we just released. And this is another example when it comes to driving under snowy and evening time period in Finland. So what is next? So we are going to extend this data set to other seasons, because this one on the left is only for snowy, but now we have another release which is going to come in the upcoming months, where we have also data coming from cloudy days, sunny days and so on. So, and we would like to see the domain shift. This is one of the challenges that autonomous vehicles are they will face. So how can we transfer the information from one vehicle to another one? So that's all from my side. I know I'm a bit quick, sorry for that, but if there is any question.
Thank you very much, Professor Aksoy. We will have some time in the end for questions.
Okay, then I will
if that's
stop
okay.
sharing now.
Thank you. We will move to the next presentation now. And I would like to introduce the third speaker, who is Alberto Giusto, a researcher in CCAM at Tecnalia. Tecnalia is a partner in events. Alberto's background is a bachelor's in electronic and industrial automation engineering and a master's in mechatronics engineering. And currently he's a PhD candidate in electronics and advanced electronic systems and intelligent systems at the University of Alcalá, with research focus on autonomous vehicles, robotics and computer vision, deep learning, scene understanding. The title of his doctoral thesis is Cooperative Perception System based on Deep Learning and V2X, an infrastructure vehicle approach. And his presentation today will be Predict to Protect, enhancing CCAM applications through V2X aided motion prediction. Thank you very much, Alberto. The floor is yours.
Okay, thank you so much, Elena. I will share my screen first. Okay. Do you see my screen?
Yes.
Yes, Alberto.
Okay. First, I would like to thank all the people from ICCS for inviting me to this webinar, and yeah, also for the nice introduction. So without further ado, I would like to present to you our work in events as Tecnalia team, which is Predict to Protect, enhancing CCAM applications through V2X aided motion prediction. Okay, yes. So I will skip this part because the introduction was given already. So a little table of contents of what will be explained in the further slides here. First of all, a little context of how autonomous driving is evolving in terms of levels of autonomy and how we are not yet to the point we would like to be in terms of levels of automation. And this means that there's still some gap in autonomous driving to get to higher levels of automation, but just not based only on a stronger onboard perception systems. But the next step will be through V2X, as Bill mentioned in his presentation before. First of all, I would like to talk a little bit about Carla. It was mentioned in the previous presentations, but I think it's important to point out like the amount of reproducible scenarios that can be done within Carla and how different risk scenarios can be reproducible inside of this simulator, and the quite relevancy of it in terms of testbed for perception, prediction, V2X research, and that's our main focus in events project. The goal of any perception system is to build a reliable, real-time understanding of the environments using different types of sensors, cameras, LiDAR, radar, GNSS, and some others as well. But there are, of course, some challenges. As Bill mentioned also in his presentation, occlusions, blind spots, and physical induced scenarios can lead to risky situations for not only for autonomous vehicles, but also for human drivers in overall. So that's why we think that there's multiple ways to enhance this. And the main focus of our presentation is motion prediction. Like human drivers, we tend to drive more predictively rather than reactively. And that's the safer way of driving. And that's what autonomous vehicles should apply as well, not just to detect what's in your surroundings, but trying to predict what they are heading to. In terms of B2X and how B2X can enhance the situational awareness of the agents in the driving scenarios, we think that it's fundamental to have it, because it can lead to collision avoidance, cooperative lane merging, intersection management, and some other many applications for CCAM. Our main role in the events project was different developments related to motion prediction and also motion planning in 3 different experiments during the events project that are platoon split management in a roundabout. That's the one that I will be focusing more in this presentation. And then the other 2, which are decision making for motion planning roadwork scenarios, and then the latest one that is motion prediction in a high traffic scenario as well. So regarding the scenario for this experiment in particular, it's a platoon split management in a roundabout where different vehicles are going in harmony in a traffic related scenario. So the whole point of it was that the connected vehicles should perceive what's around them, and not only to detect, but also to predict where they are heading in terms of, okay, there might be a vehicle entering the roundabout, and splitting that platoon information, so how the vehicles can adapt and still get back to that harmonial maneuvering inside of the roundabout. So for that, we created our own digital twin of our test stack in Technalia, and then later on I will explain to you a little bit more on detail what we implemented here. But firstly, in terms of the simulated part, we developed a whole vehicle perception stack in Carla, just training LiDAR data for an object detector, and then applying multi-object tracking algorithm in order to have a good understanding of the whole surroundings just by one single vehicle based solutions. And then from those tracked objects, we take them as an input for our motion prediction model. We train HIVT, which corresponds to hierarchical vector transformer. Is a state-of-the-art motion prediction model that we train without HDMAP in Argoverse 1. So we took into account the 20 past observations, so the 2 previous seconds observations, in order to predict what's ahead in the future 3 seconds. And HIVT gives 6 different trajectories with different confidences probabilities, so 30 samples per trajectory. You can see here the whole implementation of the perception stack, so including the object detection, the multi-object tracking, and the motion prediction. I hope you can see it well, the future trajectories that are represented in red. So this is basically the whole perception stack, but just for one vehicle. And our goal was to not just implementing one vehicle, but to show how this motion prediction model can be enhanced through cooperative inputs from other agents. So by that, we shared information through ETSI standardized messages like CAM and CPM messages. So the vehicles can be capable of sharing that that information, not just positions and speeds of each connected vehicle, but also what they are capable of perceiving around. And that led to a lot of developments that we did, and we also wrote some publications. This one example, B2B, a late fusion cooperative framework in B2B scenarios. This paper was defended last year at the Intelligent Vehicle Symposium in Romania, and the objective was to analyze the whole pipeline that we developed during events in an online method way. So just fusing the inputs from multiple vehicles and see how communication degradations can affect the predictions in different scenarios. So we tested out in Carla setups and also in real world data sets. This is one example of the whole pipeline, just in B2X Real. So this is a real world data and data set, cooperative world data set, where you could find different cooperative scenarios where vehicles are entering, for instance, in this case, an intersection, and we managed to analyze and to fuse the information from different agents in a particular scene and see how, in a real-time framework, how the cooperative fusion implies the improvement of motion prediction and thus the safer way of driving, because it will enhance the motion planning systems later on. So to test this in the end, for events, we set up a hybrid experiment, mixing our digital twin of our test track and also a fully sensorized automated Renault Twizy that we have in our lab, that it's going autonomously in our test track with AutoWare. The vehicle is sending its position through V2X to the simulator, and you can see here that well, the videos are not synchronized, but this vehicle is the Renault Twizy going inside of the roundabout, and the rest of the vehicles are virtual vehicles sharing their perception information in order to check whether the platooning split is successful or not when a dummy vehicle in Carla enters into the roundabout and let's say splits that formation. And then through the V2X motion prediction, that's fed to the motion planning all in the simulation side, and then later on the control commands are sent to the real vehicle. And then finally, we managed to test our whole framework using simulated and real world data collected during the project. And especially the whole point was the hybrid evaluation, because we managed to see the impact of the cooperative motion prediction on, let's say, in an end-to-end base, so we can see how it affects the control of a real testing vehicle. And finally, the conclusions that we got from events, at least from Tecnalia side, was the advantages of cooperative motion prediction. We have integrated the algorithm across multiple scenarios, as I mentioned before, in the other experiments in events as well, apart from experiment 2. And we proved that the algorithm is applicable to different domains beyond a particular data set. And we managed to apply this motion prediction approach in different scenarios, in different connect use cases. So that's pretty much it. And thank you, everyone. And I'm pleased to answer your questions later on.
Thank you. Thank you very much, Alberto. We will now move to the next presentation, which will be given by Georgios Kolionis, a research project manager at Exus AI Labs, with an academic background in applied mathematics. Georgios' professional background is primarily academic and research oriented, with a strong focus on systems thinking, modeling, and decision support in complex socio-technical systems. He's currently involved in several Horizon Europe initiatives, including the FRODO project in CCAM, where he focuses on operational and deployment-oriented aspects. Georgios also represents the integrated CCAM technologies cluster, contributing to cross-project dialogue on how advanced technologies can support safe, scalable, and trustworthy CCAM deployment. His work emphasizes sense-making and translating complex technical results into actionable insights for decision makers. And today, his presentation will be on maintaining awareness in a dynamic world, robust sensing for CCAM ODDs. Please, you can have the floor.
Well, thank you very much for the invitation. And I would like to apologize in advance because I'm a little bit sick and I have a terrible cough. So if from time to time I need to mute myself for a few seconds, I apologize. So today I would like to talk about robust sensing from a slightly different angle than focusing on sensors, algorithms, or system architectures. Instead, I would like to focus on the idea of awareness, how CCAM systems understand the world they operate in, and how that understanding can be maintained in a world that is constantly changing. I will draw some insights from the FRODO projects and from discussion within the integrated CCAM technologies cluster, but I will actually intentionally keep the discussion high level and reflective. So CCAM systems do not operate in a stable or a predictable environment. Roads change, weather changes, traffic patterns change, infrastructure availability changes, and actually human behavior changes. And this often happens in subtle ways rather than abrupt ones. So in such a context, technical performance alone is not enough. A system may function perfectly under expected conditions, but still fail when it loses track of what kind of situation it is actually in. This is why situational awareness, in my opinion, is one of the most fundamental challenges for CCAM as we move toward real-world deployment. Operational design domains, of course, are absolutely essential. It is them that they provide the clear definitions of the conditions under which an automated system is intended to operate safely. ODDs allow us to reason about safety, certification, and responsibility. Without them, large-scale deployment would not even be possible. So the point here is not to question the importance of ODDs, but to reflect on how they behave in the real world. The challenge is that ODDs are often treated as fixed boundaries. But on the other side, the real world is continuously evolving. Conditions do not usually change abruptly from inside an ODD to outside an ODD. They drift. Visibility degrades gradually. Traffic behavior slowly shifts. Infrastructure various infrastructure constraints emerge over time. So the critical issue is not just defining ODDs, but detecting when reality is drifting away from the assumptions behind them and reacting appropriately. This is where awareness becomes more important than a single sensing capability, in my opinion. When we talk about robust sensing, there is sometimes an implicit assumption that the solution is simply to add more sensors or improve accuracy or various other indicators. But in my opinion, robustness is less about quantity and more about confidence. Confidence that what the system perceives is consistent, contextualized, and still valid given the current situation. So robust sensing in that sense is about recognizing ambiguity, cross-checking information, and understanding when certainty should decrease rather than increase. Another key point is that situational awareness cannot realistically be maintained by a single component or actor. Vehicles see part of the world, infrastructure sees another part, traffic management systems and authorities have a broader, often strategic view. Awareness emerges from how these perspectives relate to each other over time. So when we talk about robust sensing, we are really talking about some type of distributed awareness rather than isolated perception. And with the Frodo project, this idea of awareness is explored in the context of continuity rather than isolated performance. We try to focus on how systems behave as conditions evolve, how uncertainty is recognized, how transitions are handled, and how awareness can be maintained rather than assumed. The emphasis is not on individual sensors or algorithms, but on understanding when systems should adapt, warn, or limit operation as conditions change. Digital twins are often discussed in technical terms, but how I see them primarily is as awareness mirrors. They provide a shared evolving picture of the system and its environment, a picture that humans can understand and reason about. And this is particularly important for operators and authorities who actually need to understand not only what the system is doing, but why it is doing it and how conditions are evolving over time. Through the integrated CCAM technologies cluster, of course, projects. It includes 8 EU-funded projects. Of course, remaining fully independent in their objectives and implementation. The value of the cluster is not integration; it is reflection. But by comparing approaches and experiences or common challenges. Very interesting results become visible, especially around awareness, robustness, and the transition from pilots to actual deployment. And this shared reflection helps us understand patterns that are not visible within individual projects alone. Actually, one of the striking observations across all those CCAM projects is that very different technical approaches often converge on similar conclusions. Awareness needs to be continuous, not static. Robust sensing supports trust and explainability, not just performance. And deployment challenges are often organizational and operational rather than purely technical. These lessons are emerging regardless of the specific technologies involved. Why all this matters? because actually large-scale deployment depends on more than technical capability. Authorities need confidence that systems understand their operational contexts. Operators need transparency and predictability, and the public needs trust. So in that sense, robust awareness acts as a bridge between technology, governance, and societal acceptance. And without it, scaling CCAM will remain difficult, in my opinion. So I would like to close with one key message. CCAM success depends less on how well systems see and more on how well they know when they should not trust what they see. Thank you very much, and I look forward to the discussion.
Thank you very much for the nice presentation. We will move to the last presentation of today's webinar, which will be held by Yorgos Zacharopoulos. Yorgos is project manager of the Podium project and a scientific project manager for ICCS since 2024. He has worked as a senior ITS advisor for the English motorway operator and as an ITS consultant for Mott MacDonald in the UK. He holds a master's in electronic and electrical engineering from the University of Strathclyde. And today he will speak about CCAM challenges towards large-scale deployment. Thank you very much, Yorgos.
Thank you, Elena. Please let me know if you can see my slides.
Yes, we can.
Okay, great. Right. Good afternoon, everyone. Many thanks to the Events Project for giving me the chance to present some elements of Project Podium as part of this webinar. As Elena mentioned, my name is Yorgos Zacharopoulos. I'm a scientific project manager for ICCS, and for more than a year now, I have the role of the day-to-day manager of Project Podium. And today I will focus on the first part of the webinar title about CCAM challenges, and I will try to highlight how these could affect large-scale deployment. But firstly, just a few words about Project Podium. So Podium stands for Physical Digital Infrastructure or PDI connectivity and cooperation enablers building trust and sustainability for CCAM. It's an Horizon Europe project that started in 2022, similar to Events, and ran until the end of 2025, meaning last month. We brought together 26 partners from 8 different countries with a total budget of 12 million euros. And the project is coordinated by ICCS in Greece and Mr. Amditis. And the project focuses on enabling connected and cooperative automated mobility by strengthening both physical and digital infrastructure, while also addressing trust, data integrity, and sustainability aspects. The objectives of Podium might look broad, but they all focus on enabling CCAM in real traffic conditions. First, we aim to identify and assess key connectivity and cooperation enablers needed for CCAM deployment. We also advanced and demonstrated technologies such as multi-connectivity, hybrid data management, and multi-access edge computing, which are essential for low latency and reliable services. Another critical objective was system trust. In other words, ensuring data truthfulness and software integrity across our CCAM ecosystem. And finally, we demonstrated all these through 5 use cases in 3 living labs, while also delivering a flexible reference architecture and contributing, of course, to policy and standardization discussions at the EU level. Right. A few words about our living labs. We split our work into 3 different living labs, one in Germany with 1 use case, one in Spain with 2 use cases, and one in Italy with another 2 use cases. The German Living Lab was based in the city of Ulm, where use case 1 focused on cooperative corridor management, and its demo took place back in April. The Spanish Living Lab included 2 use cases, as I mentioned. Use case 2 was based in the city center of Barcelona and focused on urban traffic environments by creating a CCAM corridor within the city with a focus on emergency vehicles. And use case 3 was based on C32 motorway just outside Barcelona, and focused on creating a simulation of a CCAM cross-border corridor and a mobility as a service solution. In our case, that was supposed to be between the borders of Spain and France. The Spanish Living Lab demos took place back in November alongside our final event. The Italian Living Lab also included 2 use cases. Use case 4 was based in the city of Turin and focused on trusted cooperative perception for intersection maneuver assistance. And lastly, use case 5 was based on the A22 motorway of Autostrada del Brennero at the north of Italy and focused on the risk management within a highway tunnel. Both of these use cases were demonstrated back in October in the city of Turin. Overall, these living labs allowed us to test not just the technology, but also regulatory, operational, and societal aspects in realistic conditions, real traffic. Now moving on to the challenges part. One of the most fundamental challenges towards large-scale CCAM deployment is the integration of multiple technological layers into a single coherent system. In Podium, we were not just deploying individual components, but trying to integrate multi-access edge computing, digital twin technologies with roadside units, in-vehicle data sources, and vulnerable road user data sources as well. Each of these elements has different latencies, reliability issues, and data quality requirements, which made it challenging. A key difficulty was also to maintain consistently low latency while at the same time supporting the platforms that we developed and the services, such as multi-connectivity and the hybrid data management and software integrity and data trust mechanisms. And these services are really essential, but they are also introducing additional processing effort and coordination, of course. Another important aspect was interoperability. Many of the systems we interacted with are sometimes legacy systems, especially on the traffic management side, and some of them were not originally designed to support CCAM use cases. So that created another challenge. And finally, scalability remains, of course, a major concern. Even within Podium, integrating and operating across 3 living labs already required significant effort. So scaling these solutions to city-wide or even national wide deployments would require much more in terms of technical maturity, but also in terms of operational coordination and long-term infrastructure planning. Moving on, beyond technology, regulatory challenges, and particularly related to automated driving permissions, can have a significant impact in deployment timelines. One of the main issues that we faced was the lack of a unified approach to automated driving testing across the EU member states. Every country applies different rules, has different documentation requirements and approval processes, and that makes cross-border projects and use cases like ours particularly complex. In several cases, requirements from the national transport ministries were not completely defined, were not fully defined. That led to a repetitive clarification process during the project. And following that, we faced also interlinked approval chains. For example, approval from a national authority would trigger then additional requirements at a regional or a city level. As a result, the liaison with authorities sometimes was challenging, especially where there was absence of clearly designated contact points, let's say. Delays, of course, in those permissions obviously had an impact in the availability of our vehicles, the infrastructure that we needed to deploy, and scheduling our trials. Now, with regards to testing and trialing CCAM systems in real traffic conditions, that introduces different challenges that go a little bit beyond any in-lab development. One issue relates actually to vehicle insurance. So insurance framework for automated driving test vehicles are not harmonized across the EU countries, which complicates planning and cross-border demonstrations, as we mentioned earlier. And then aligning test protocols with local traffic management operators was also quite demanding. Each operator has had its own procedures, priorities, and technical limitations, which of course must be respected when we design our trials. We also experienced delays in regulatory approvals for the deployment of roadside units, for example, that took place in Autostrada del Brennero, especially when temporary road closures are required. Of course, these approvals, most of the times require multiple approvals, dependencies from multiple stakeholders, and long times to be completed. Finally, the availability of safe and controlled traffic conditions often limited our ability to execute planned scenarios exactly as we had designed them, requiring some flexibility and contingency planning through those trials. Then about public impact and acceptance. Apart from the ones that we have discussed so far, we noticed that during trials and demos, we observed that even some relatively minor traffic disruptions, such as a temporary lane closure, for example, could lead to frustration among road users, despite the fact that we had tried earlier to communicate the efforts of the project and what we are trying to achieve, etc. And for us, this highlights the importance of managing expectations really and clearly communicating the purpose and long-term benefits of CCAM trials to the public. In some cases, we also encountered limited engagement from local authority representatives that were not convinced to attend the demonstrations even within their areas. And although Podium has invested significantly in dissemination activities across multiple channels, reaching to wider audiences beyond just the research and professional community of this industry, that remains a challenge. It's not easy to achieve. These experiences really underline the fact that public trust and acceptance are not just an automated outcome, let's say, of technical success. That's one thing, but also requires constant engagement and transparency and evidence really to the public that the CCAM solutions have actually societal benefits. And one last thing, I thought to give some recommendations also. And based on this experience, firstly, there is a clear need from our perspective for better regulatory and permit alignment, including well-defined guidelines, timelines, and contact points, of course, for any automated driving pilots. Ideally, of course, harmonized across the EU. Secondly, we need targeted infrastructure investment, particularly for deploying advanced technologies like multi-access edge computing at specific junctions or traffic points. Thirdly, extending and replicating test corridors in urban areas, highways and tunnels would definitely support future CCAM large-scale deployments. And finally, public engagement and trust should be strengthened by leveraging user acceptance and socioeconomic evaluation results from various CCAM projects and use them as a basis for local engagement strategies that will also support large-scale deployment of CCAM solutions. And that is all really from me. Thank you very much for your time and attention. And I guess if there are any questions later, I'm more than happy to answer.
Thank you very much, Yorgo. With this presentation, the webinar of today concludes. We have some time, not much, for questions. So I would like first to ask the audience if there are any questions that you would like to raise. Okay. Yes, Irini.
Hello, everyone. I'm Irini from Events Project. I have a question for Elena Aksoy, for Professor Aksoy. He mentioned something. He mentioned about several obstacles. So I was wondering what are the primary ones, the main ones hindering the deployment of automated vehicles in adverse weather conditions. It was not clear to me. So.
Yeah, there are multiple, but if I'm allowed to list, maybe I can definitely say as the first one is the lack of data sets. So all these data sets available right now in the literature, they are captured mainly under clean data. We have a very nice table. I did not show it, but we reviewed all those public data sets, and those that were published very recently, even if they claim like they have, for instance, snowy condition, it was just like, let's say 2% of the entire data set, which sometimes corresponds to only like 400 frames, 200 frames. It's just not enough at all. So data, not only data, but also annotation of the data is a big obstacle. And another thing is like, even if you have a data set for one vehicle type, so can we now transfer all this information to another vehicle, let's say to a truck? So we call it domain shift. So you have a change in your vehicle, in your setup. Even if you have the very same vehicle, let's say when you change the pose of the camera or the LiDAR sensor, let's say you are tilting it a bit because of the configuration issues, then the quality of the data changes. So whatever you annotated in the for the first car will not apply to this new car. So there is a shift between the vehicles or between the domains. So this needs to be addressed somehow. And scientifically, there is not that many works addressing this problem. So those are like, let's say, two main issues that we were also struggling a lot in the project. And also, of course, there are legal issues like how can we verify that the system is ready and the responsibilities and all that. Did I answer your question, Irene?
Yes, thank you, Professor Axel.
Thank you very much. I would also like to ask a question to Alberto. How can drivers and autonomous vehicles become more predictive in their driving behavior? Can we work on that, especially with autonomous vehicles?
Indeed, it's a topic that, let's say, it never ends, because it's not just only applied to autonomous vehicles, as you mentioned, but also to human drivers. Like, our way of driving should be more, like in most of these scenarios, should be more predictive than reactive, because otherwise we'll be just clutching the brakes the whole time. But I think that automated vehicles should be more predictive in terms of adapting to different scenarios through V2X. I think in V2X it's a key factor to not just be more predictive in your way of driving. It can be ADAS for your particular vehicle, or an automated system in overall, but also I think it's a safer way, because it can lead to prevent a lot of collisions and a lot of risky situations.
Yes, thank you. Thank you very much for your answer. If no other questions, I would like to ask a question to Georgios Kolionis first. I would like to ask, in your opinion, what are the biggest obstacles in maintaining situational awareness now that CCAM systems start moving from pilots to real-world deployments?
Thank you for the question. It's actually this that I was trying to communicate today. In my opinion, the biggest obstacles are not purely technical. They are systemic and operational. First of all, that real-world variability is far greater than what pilots usually capture, because in pilots the conditions are partially controlled, while in deployment environments, as I was saying, contrary to the pilots where the conditions are partially controlled in deployment environments, weather, traffic behavior, infrastructure availability, all these chains. Also the fact of the fragmentation of situational awareness, the fact that different actors like vehicles, operators, traffic managers, authorities, each see only part of the picture. That's, in my opinion, quite a big obstacle. The fact that systems struggle with recognizing uncertainty and degradation. And there are also, of course, organizational and governance barriers that would be among the biggest obstacles.
Thank you. Maybe to continue with the same on the same line, I would ask Yorgos Zacharopoulos this time. From your experience with Podium, did you face a challenge that you think is a very important one that affects large-scale deployments?
Yes, actually, I think the challenge that I mentioned earlier about the consistency in regulations and permits and the guidelines from national authorities and or local authorities is actually quite important. And I think if we have like a European framework around that, that would help us a lot. In our occasion, it was a great challenge, mostly because our OEM was coming from France and they needed to operate within Spain, and there was a problematic situation there with the permissions that we needed to receive from the Spanish authorities. And as I mentioned, that triggered chain requirements from the local authorities. So plus the insurance policies that they couldn't align between different countries. So yes, I think that was the most significant one that we all felt within the project, that if we are facing that while trying to test specific solutions and technologies, what would happen if we are trying to move to a larger scale deployment of any CCAM solutions? That would be that would make it really difficult.
Understood. Yes. Thank you. Thank you very much. I would like to ask one question as well to Bill. Do you foresee your hybrid validation approach being integrated into OEM or regulatory testing workflows?
Thank you, Elena. Well, yes, and I believe that's actually the motivation behind our work in this hybrid setup, in the sense that it is scalable, it is repeatable, it is adaptable to different configurations. So industry players, eventually, whether it would be our solution or someone else's similar solution, but using such a hybrid validation will help them a lot into benchmarking cooperative perception algorithms in a standardized way before deploying them in a real world setup. And this kind of this hybrid configuration will help them immensely in reducing the testing costs and also improve their reproducibility of the results. So I believe in all it's really a solution that it's a win, a great win for industry players to test different algorithms in a very cost-effective and safe way.
Yes.
That's it. And just to, I don't know if we are finished with the questions, but in any case, I would like just to share the, let's say, the banner of our final event, and I will just leave it there, and if there is other questions.
Thank you. So 25th of February in Delft. Is there any other question? If not, I think that we can conclude this webinar. If there are more questions, feel free to address them to Bill or yes, Irini?
Yes, Elena, if you allow me,
Sure.
just 1 minute. Elena, I will share the connection link, the registration link for the final event of events. It will take place in Delft, but also online, and we would be delighted.
I think she already did in the chat. Yes, thank you.
I think
yes,
Irini's connection dropped probably.
okay. There
Yeah,
seems
just
to
to
be an
finalize
issue
it.
here in
So
Greece.
yes, Elena, as you said, the other Elena Krikiliani, shared the registration link for our final event, and as Irini already said, of course, we'll have a physical presence there, but the presentations will also be online. Although for whoever is close by, we're really happy to have you there, because we will also have two real vehicle demos. One only perception, but the second one will be perception and decision making and control, so it will be a full autonomous demonstration. And this, due to technical difficulties, won't be able to stream online, so we'll only stream online the presentations. And then we'll go to the outside the testing area to see the vehicles, but this will not be included in the online streaming. So of course you can we'll be very happy to have you online, but even better in a physical presence. That's all from me.
Thank you. Yes, it will be an amazing final event, I think. And I think that it's time to conclude this webinar if there are no more questions or discussion points. And if there is anything that comes up later, you can always reach out to Bill for questions, or to the other presenters.
Absolutely.
Thank you all very much for being here
Thank
today.
you, everybody, for joining, and special thanks to our presenters.
Special thanks to the presenters, exactly. And we wish you a happy afternoon and a nice day.